Thanks. Thank you also for the introduction. I'm going to talk about a different topic. So it's about post-processing. There will be several more talks and posters as well about post-processing. So I'll be talking about multivariate post-processing of ensemble forecasts and making multivariate probabilistic forecasts. This is mainly work done by Jigu Chen, one of my PhD students, and we did this in joint work with colleagues at the University of Darmstadt in Germany. So I'm sure that many of you are aware that ensemble weather forecasts are a great tool for weather forecasting, but despite continued improvements over the past decades, they are still subject to systematic errors. I've brought you two examples here. So these are ensemble forecasts of temperature by ECMWF at a station at Frankfurt Airport. And you can see typical examples that these ensemble forecasts make. So on the left-hand side here, you have 50 gray lines. These are the 50 ensemble forecasts, and you have the red line, which are the corresponding observations. And here, sometime in March 2016, you can very clearly see that the ensemble forecasts are biased and they are too low by a couple of degrees Celsius. Now, second example here, same data set, I just picked a different period of time, and you can see that here the ensemble forecasts don't have a systematic bias over time, but you can see a different problem, which is that the uncertainty in the ensemble is clearly underestimated and is too small, and the red line of the observation typically lands outside of this uncertainty band of the ensemble. So the ensemble is not well calibrated and underestimates the true forecast uncertainty. And these are very typical errors that occur for forecasts from many different systems or many different equations, many different variables, sorry. And that's why post-processing is needed. So post-processing is now where statistics comes in, and post-processing is the process of using statistical or machine learning models to correct these errors that you saw before. So one example approach from more sort of statistics perspective is called ensemble model output statistics, or EMOS in short. So the idea is to use a parametric model for the conditional distribution of the observation Y given forecasts. So this X is a set of ensemble forecasts. For example, ensemble forecast of that same variable. And we model that conditional distribution by a parametric distribution, and the parameters are then linked to summary statistics from the ensemble system. So, for example, if we would want to model temperature, want to build an EMOS model for temperature, what we would do is we have our ensemble forecast of temperature, and we want to model temperature observation given the ensemble forecast of temperature. We could do this, for example, by picking a Gaussian distribution, which may be a reasonable assumption for temperature, which means that we have two parameters, location parameter mu and a scale parameter sigma, and then we need to link those parameters to the ensemble forecast of temperature. For example, by picking a linear link function in the ensemble mean and a linear link function in the ensemble standard deviation for the location and the scale parameter. And then these coefficients A, B, C, and D are our actual model parameters that we need to estimate from past training data in order to correct errors in the mean or in the standard deviation. And these models have been now used for something like 15 or 20 years, and they tend to work well. Post-processing using these statistical models has become a standard practice in research, but also at weather services. However, there are some challenges when considering this, for example, this EMOS approach to post-processing. And this mainly comes in when you think back to this equation, to this set of equations here, because of course, as output of our physical models, we have ensemble forecasts not only of temperature, but we have ensemble forecasts of many other variables that also potentially have some information about temperature, things like wind speed, solar radiation, precipitation, and so on. And we maybe want to include them in the model here, but this means we would have to specify this link function by hand to decide how our distribution parameters should depend on all the possible input predictors. And this becomes very difficult, especially if we have many possible predictors available. And one of the ways to overcome this challenge would be to use a neural network for doing this. So this is joint work that I did some time ago with Stefan Rasp, who back then was a PhD student. And we propose to use a neural network for doing this distribution regression task. And essentially, we estimate the parameters of a parametric distribution directly as the output of a neural network. And this allows to learn arbitrary nonlinear relations between the inputs and the distribution parameters in a data-driven way, not having to specify these link functions by hand. And we use a sort of different tools, for example, to be able to allow estimation of one model jointly for many locations, but still having that model to be locally adaptive. Before quickly showing some results for this model, I want to show you the data that I'll be using in my talk today. So this will actually be two data sets, which are very similar though. So one is for temperature and one is for wind speed. And we have ECMWF forecasts that were made 2 days in advance. We have 50 member ensemble forecasts of in total 18 variables, which we reduced to mean and standard deviation. We have data from around 500 stations for temperature and I think around 200 stations for wind speed over Germany, and we have 10 years of data. And we used the first 9 years for training and the last year for evaluation purposes. Now, taking a very brief look at these distribution regression models based on neural networks that we proposed, this is how they look like. So these are fairly simple, feed-forward, fully connected neural network models. The output are the distribution parameters of the forecast distribution. So for temperature, this is just a normal distribution. We predict location and scale parameter of that distribution. For wind speed, we use a truncated normal distribution to ensure that we only put positive probability on positive values. And as inputs, we use forecasts from the physical model. So these are these yellow ones. So we have these 18 variables. We reduce them to mean and standard deviation and use that as input to the model. We have information about the stations, things like coordinate, altitude of the station. And we have a feature that's called station embeddings here. So this is a mapping from the individual stations IDs to vectors of latent features that are then used as additional inputs to the model. And this serves to make the model locally adaptive when we train one model jointly for all stations. Now, one key feature is that as a loss function, we use the CRPS, which is a proper scoring goal that is tailored towards the task at hand. So producing a distribution forecast for a real valued observation. And just as a very brief look at the results, you can see here, going back to the example from before, that this works. So here, these blue lines are now a post-processed ensemble. So I've applied our neural network-based post-processing model, and I've generated an ensemble by just drawing quantiles from the distribution. You can see bias is removed and the uncertainty is increased so that now the red line of the observations lands inside this uncertainty band most of the times. So this works. This also works more quantitatively, so you can look at the paper to see many more results. But that's not what I actually wanted to focus on today, because today I want to talk about multivariate post-processing, because everything I've talked about thus far and lots of the things that have been done in research on post-processing has focused on univariate methods. So considering one target variable, one forecast lead time, and one location at a time. But many applications require not only univariate forecasts, but they also require accurate models of dependencies. That could be spatial dependencies or temporal dependencies or dependencies between different variables. But when we now apply post-processing separately, for example, for different variables, then we lose those dependencies. Key examples where these dependencies are important, though, are, for example, energy forecasting, where, for example, it's very important to have temporally consistent forecasts of the available energy or energy production, but also forecasts that are consistent between different variables. For example, in Germany, there has been lots of discussion about so-called Dunkelflauten, so periods where you have low wind energy production and low solar energy production at the same time, which would not be good. Another key example are hydrological applications. You may have a situation like it's shown here. So you have different valleys, and every valley is feeding one river that all go into one reservoir. And if there's heavy rainfall in only one of those valleys, that may not be a problem. But if there's heavy rainfall simultaneously in all of those valleys, that may pose a problem, and the dam may not hold the water coming to the reservoir. So it's not only important to know the marginal probabilities, but also the joint probabilities to have the multivariate dependencies correct. So how would we go from univariate post-processing to multivariate post-processing? And the state-of-the-art way of doing this would be so-called two-step models. And they proceed by separately modeling the univariate distributions and the multivariate dependencies. It means that in the first step, we do what I just talked about. So we perform this univariate post-processing. For example, using EMOS approach, or if we want to use machine learning approach, we could use this distributional regression model based on a neural network that we proposed. And this will give us a univariate forecast distribution for every variable at every location. And we can then produce, for example, a sample, a post-processed ensemble. but we've lost all information about dependencies if we do this. So in the second step, we then have to restore these multivariate dependencies using copular-based methods. So in principle, what one is doing is then one just reorders the sample values produced in the first step according to some dependence template by imposing the dependence structure from, for example, the raw ensemble forecasts, or from past observations, or using some sort of parametric model that involves past observations. So there are different approaches for doing this. There have been some studies that compare those, and they typically find that they more or less all work equally well. Differences in performance are generally small. So why am I still standing here, and why am I talking about alternative ways of doing this? The reason for this is that these state-of-the-art methods, they show some common limitations. And most importantly, in my view, is that there is no straightforward way to include additional predictors in the second step of modeling the multivariate dependencies. In the univariate models, we can do this using, for example, these neural network models I showed you. But in the second step, where we restore the dependencies via copulars, there is no straightforward way of including information from other variables. But since this has been one of the key efforts to improve the univariate forecast, it's also likely that this may also lead to multivariate improvements. As a second disadvantage or limitation is that the number of samples that we can generate from the multivariate distribution is limited. For example, if we want to use this ensemble copular coupling ECC approach by the size of the ensemble, or if we use those based on historic data sets, then that's limited by the size of the historic data set. And to address these limitations, we propose a new method for multivariate post-processing using generative machine learning. And here, samples from the multivariate forecast distribution are directly obtained as the output of a generative neural network, which allows to now include arbitrary input predictors, not just forecasts of the target variable. And further, we circumvent this two-step structure of the traditional methods and simultaneously model marginal and multivariate dependencies. And as a side effect, we can generate an arbitrary number of samples from the forecast distribution, not just the number of ensemble members as before. So to very briefly give you the basic idea of generative machine learning, I brought some pictures here. And while these look like ordinary human faces, they are all not. So they are all generated by a machine learning model. Now, with all the developments that have been going on, this is not sort of impressive or surprising anymore that you can do this with machine learning. But when I would show these slides just 2 years ago, people were also very impressed by these faces that look like human faces, but are AI generated. Nonetheless, these underlying ideas of generative machine learning are still very interesting. So generative machine learning, as many of you will know, aims at learning properties underlying some sort of training data set to generate realistic new data. And here we are interested specifically in so-called implicit generative models. So these are models that aim to provide a representation of that probability distribution by defining a procedure to generate samples from that distribution. So what we want to do is we want to generate samples of here arbitrary size from our multivariate forecast distribution. And a simple generative model would just take as an input samples from some simple base distribution. This could just be a uniform distribution or a multivariate normal distribution, and would put out samples from the distribution underlying the training data set. And of course, the interesting part is then this map here that maps these noise inputs to samples that we are interested in, and this is parameterized via a neural network. And one class of generative models that have received lots of results, that is GANs, so generative adversarial networks. They have been mostly used for image processing and show great results for this task. You will also see, I think, one more talk at least and some posters where GANs are being used. But their training tends to be challenging. So this is why we are looking at a different class of generative models. We call them scoring rule-based conditional generative models. The underlying idea comes from these generative moment matching networks. That's a sort of subclass of alternative generative approaches. And the core idea here is to replace the discriminator part of a GAN by the maximum mean discrepancy, so a kernel-based two-sample test statistic to measure distances in the space of probability distributions. We take these ideas, you can find all the details in this paper here below, and we adapt this first because we are interested in making this conditional on other inputs. So the inputs to our generative models will not just be these latent noise variables Z, but we will also have our additional inputs X, and this will be the ensemble forecasts of all the different variables that we are that we have available as input to our model. The second, we also adjust the loss function in the model because we will be using the energy score. The energy score is a multivariate proper scoring goal. It's a generalization of the CRPS to higher dimensional cases to train this conditional generative model. And yeah, this has some theoretical connections to this MMD metric. But in principle, this energy score is a specific loss function that is very much tailored again to the task at hand, which is making multivariate forecasts in the form of a sample from a forecast distribution and evaluating this against the multivariate observation. So that's how our models look like. This looks a bit complicated at first, but I'll try to walk you through the main idea. So as output of the model, we produce samples from the multivariate forecast distribution. So these are these yi hats here. And they are composed of two components. They are composed of a mean component and a noise component. And then we apply a soft plus activation function if we want to model wind speed to ensure that we really get just positive values. So the mean component is obtained just as a linear model, where as an input, we have ensemble mean forecasts of all variables we have available as input at the different locations. So in our case, we will always consider sets of stations, 5, 10, or 20 stations jointly. You will see this in a second. And K is the dimension of variables that we have available. So we first do some sort of deterministic bias correction to obtain this mean component of our output distribution. And the noise component is where the model becomes more interesting. And this is also where this generative structure of our model comes in. So here we have these latent inputs that we just sample from a multivariate normal distribution. And what we first do is we adjust the scale of these variables, conditional on the uncertainty information from the ensemble weather forecast. So these S here are the standard deviations in our different input variables. And we use this to estimate some sort of scale adjustment factor that adjusts the scale of the latent variables, and then conditional on all available inputs, so the means and standard deviations, location information, time information, we estimate this noise component. So these different modules of the full generative model are all learned jointly. So we just estimate all network parameters at the same time, optimizing the energy score. That's the setup that we are going to use. So using the data set that I showed you before, what we do is we randomly pick one station locations for either temperature or wind speed. So we do this separately for temperature and wind speed. And then we just select these stations that are closest to that station we picked. So to end up with 5 or 10 or 20 station sets. And then we fit our CGM, so conditional generative model, to generate a multivariate probabilistic forecast. And we do this not only for our model, but we also use different benchmarks. So we combine either EMOS or the neural network-based post-processing model for univariate forecasting with ECC and GCA. So ECC was estimating multivariate dependencies from the ensemble. GCA is from past observations, but involving some parametric assumption. But we do all of this 100 times to get some idea about the variation across these repetitions, and we summarize this via box plots. So before looking at multivariate results, we of course want to make sure that also our univariate forecasts we get out in the end still make sense. So that's what we look at here. So that's the mean CRPS, left-hand side is temperature, right-hand side is wind speed, and the raw ensemble is here black, and then just using the univariate EMOS or DRN model is purple and green, and our model will always be in red. And you can see that for temperature, it's slightly worse than using this DRN model, which would be sort of the state of the art for just doing the univariate post-processing step. But for wind speed, we're actually doing even slightly better than using this neural network-based post-processing model. So overall, our model that is not at all tailored to making good univariate forecasts also produces at the very least reasonable univariate forecasts. But we are, of course, more interested in the multivariate performance. To evaluate this, we use two scoring rules. One is the energy score, one is the variogram score, just a different multivariate proper scoring rule. And now these are lots of numbers in the large table. So the upper half is temperature, bottom half is wind speed. And I've highlighted the best values in bold text, and you can see the different columns. These are different models. and the rows are different dimensions from 5 to 20. And without focusing here at too much individual details, you can see that our model on average performs best for most of the cases. The only exception here is temperature when evaluated with an energy score, where it's competitive to the best alternatives, but slightly outperformed by, for example, this DRN model and ECC or GCA, depending on exactly which case you look at. More interesting, it's maybe to look at the variability also across these random repetitions that we performed. So here are now skill scores. So skill scores measure the improvement relative to a benchmark model. So here, larger values indicate better forecasts. Our benchmark here is always EMOS plus ECC. So for example, a value here of 0.1 would mean a 10% improvement in terms of the energy score of here, for example, these models that are all performing similarly. So bottom half is energy score, top half is energy score, sorry, bottom half is variogram score. This is all still for temperature, and you can see what essentially the table before indicated already. So for the energy score, temperature, we can see very similar results for our generative model and this sort of state-of-the-art approach of using a neural network for univariate post-processing, and then in a second step, restoring the dependencies. But if we look at the variogram score, you can see we are actually doing a bit better than these state-of-the-art methods. For wind speed, the results are a bit more clear. So for here, both energy score and variogram score, you can see substantial differences and substantial benefits to using these generative models over these two-step models, where additional information only enters at the univariate forecast. So of course, one question that we had is like, where do these improvements come from? And to assess specifically the effects of including these additional predictors, what we did is we trained also a model of our generative model that, however, doesn't use any additional predictors. And these are these gray boxes in the illustration here. So this is, I think, for dimension 10, temperature, and wind speed for these different skill scores. And here you can see that you lose quite a bit of performance, of course, when not including additional information, indicating that including these additional predictors is an important factor that contributes to the model performance. But you can also see that you are actually doing a little bit better than models in these EMOS and ECC or EMOS and GCA models that did also not have access to additional predictors. So there's also some sort of benefit of this generative structure of the model overall, potentially by having a non-parametric model for the marginal distributions as well, and not having to assume some parametric model for those. Another thing that we can do now is that we can just increase the sample size, because we can just create an arbitrary number of samples from our multivariate forecast distribution. So we are no longer limited to 50 samples. So before, everything was based on 50 samples, which is the size of the ECMWF ensemble. But now we could just go ahead and generate 500 samples. And generating more samples leads to improvements in the score. So this here is now skill scores for temperature and wind speed, but using our generative model with 50 samples as a reference. And you can see that going to something like 400 or 300 samples leads to improvements of something like 1 to 2%. So you again get some sort of small improvements by creating larger samples. One more point on this is that you have to consider different ways to generate an ensemble of these generative models. So let's say we want to generate 50 ensemble members in the end. What we could do is we could just estimate one generative model, produce 50 samples, or the other extreme case would be we estimate 50 generative models and generate one sample from the forecast distribution every time. And you can see that depending on which strategy you pick, this has a bit of an effect on the score. I think these differences are something like 5% here overall. And what we had done without looking at this before was we just estimate the model 10 times and produce 5 samples each. And you can see that's already a good compromise maybe, because of course, the more you repeat your model estimation, the higher the computational costs will be in the end, because you need to re-estimate your model. So to summarize, we propose a new multivariate post-processing model based on generative machine learning. In these case studies I showed you, we outperform state-of-the-art two-step methods. Conceptual advantages are mostly the ability to incorporate additional predictors, not having to make parametric assumptions, generating an arbitrary number of samples. Computational costs are still manageable. So for the largest dimensional case we considered, estimating this full ensemble of 10 models and producing the samples takes about 2 minutes on the GPU. So that's yeah, still very much manageable. Yeah, challenges for future work. I think one particular challenge is multivariate evaluation, because we do see these improvements in the results in the scoring rules, but it is very difficult to figure out where these come from, because they could come from improvements in univariate forecasts. It could come from better capturing multivariate dependencies. And I think there is a general lack of understanding of these tools for multivariate evaluation, especially regarding extreme events. There has been some progress, but evaluating extremes is important, especially in multivariate settings. And I think there is still a lack of understanding and appropriate tools for doing this. And generally, I think it's interesting to also look at spatial forecast fields using these generative models. And also from a more theoretical perspective, they are a very interesting class of models. And I think Lorenzo will present parts of their work later on, talking a bit about these more theoretical aspects. So there is a paper coming out soon, and there is a preprint archive with much more details. And with this, yeah, thank you for your attention.
Thank you, Sebastian. Any questions?
Hi there, thanks, very nice talk. How do you choose the kernel for your energy score, for your MMD distances?
So, we just pick the sample version of the energy score. So just the standard, so you do not have to pick any kernel then. It's just the, I maybe have the formulas. Yeah, so we just use that energy score, yeah. Yeah, that's the loss function we use. You could do much more general things, but for us, it's just the sort of standard energy score that has been used for multivariate forecast evaluation.
I guess I have a question kind of related to this. So when you do this embedding, is this at the level of the joint distribution or conditionals, or say you have a conditional model?
So you mean the embedding?
Yeah.
The embedding just takes place for the univariate models that we do. So, and try to go back to the slide. So this was for the univariate model. So we have, there it is. So that embedding went, or
yes.
So that's for the univariate models, and the so the problem is that we have data from lots of different stations, and for this EMOS model, for example, you would estimate one separate model for every station. Now, what we do for the neural network is we estimate one model jointly for all stations, but we still want to make the model locally adaptive to the properties at the individual locations. And that's what we use these embeddings for. So they just map the ID of the station to a vector of latent features, and they enter the model as additional inputs. So they serve to make the model locally adaptive. And without losing the advantage of having the availability of lots of data points to learn information from data stations jointly for the model.
Okay, thank you. Any other question?
I can speak up. So, have been standard GANs used here with a proper discriminator. Are they really doing absolutely worse than scoring rules?
So we have not compared to GANs. What we want to do this in the next step. So we want to extend this more to settings where we have spatial fields, so image-like data. I think the next talk will be on GANs. So you may have to wait for the next talk to see some comparisons. Yeah, so we haven't done this comparison. Personally, I assume that GANs are probably working better if you really have spatial domains where you have grid-like input data, where they're really tailored to. Whereas without having done the comparison, I would expect that maybe these models that are really tailored to energy score would probably also perform better in terms of the energy score if you do a one-to-one comparison. But yeah, I would have to come to the comparison.
Okay, well, thank you again, Sebastian.